Okay, so we did a little bit of introduction on how RISC works, how register instructions work, how immediate instructions work. These are, again, are both data processing instructions that take information from the register file and for immediate value instructions from the instruction itself, combine those somehow and put them back in the register file. Well, let's talk about the register file. Let's talk about what we call the programmer model, which is the register file and how memory is allocated. So the register file in RISC-V, the 32-bit integer version, is 32 registers, and they are allocated in certain sort of conventional ways. You can use any of these registers however you want, but there are standard conventions that allow things like subroutines and parameter passing and stuff like that, which it's a good idea to stick to because other code you use will also stick to those. And we'll talk in detail about the processes of parameter passing. I'm going to assume that you have a pretty good idea of how subroutines actually get called and returned, because I've got some videos on that in ARM and MIPS, and so if you're missing that stuff, you can go and check those for the basics, but I'll give you the summary of how it works in RISC-V so that you have an idea. We start at the top. These registers are named X0 through X31. These are just the basic names that equate to the register number. But each one also has a name that most assemblers will recognize. So the 0 register, for example, is X0. You can't write to this. This is a constant 0. Very useful in a lot of contexts. If you want to branch on negative, you need a constant 0 to subtract from. That's what register 0 is for. Same in MIPS. MIPS does the same thing. Register 0 is a constant 0. Register 1 is typically our return address. Register 2 is our stack pointer. Register 3 is our global pointer. Register 4 is our thread pointer. And then if you've done MIPS or ARM, you may not have been familiar with what global pointers and thread pointers will do. We'll talk about those later on. The frame pointer you're probably familiar with. That's register 8. If you're not using a stack frame, you can use that as register S0. And then we have S, T, and A registers. T registers are 5 to 7. S registers are 8 and 9. A registers 0 to 1, and then 2 to 7. S registers 2 to 11, and then T registers 3 to 6. And the question, a reasonable question is, why don't we just put all the S, T, and A registers, once we figure out what they are, why don't we put them all together? Why are they all spaced out like this? Well, again, it's for extensibility. You can make a version of this that is 16 registers instead of 32 if you want a shorter, smaller 16-bit architecture. Well, if you cut this off at 16, right, then you get the basic pointers and a few other things that you can do. If you extend it all the way to 32, then you get these extra argument and saved and temporary registers that you can fill in. And then there's a 64 register version of this as well that you can extend into. So that's why they're sort of jumbled around a little bit for extensibility and customization. So what are the S, A, and T registers? So they are, besides the specific registers, return addresses, pointers, and stuff, we have saved registers that are labeled S. We have A registers that are labeled A. Those are arguments and also can be used as return values. And then we have T registers, which are temporary. And the main difference is whose responsibility is it to make sure that data is preserved. If you are writing a subroutine, and within the subroutine you want to use some registers, you got to know which registers you can mess with and which registers the caller expects to be the same after the call, right? Like if you're running along and you do a jump to subroutine, for example, then after that jump to subroutine, in the next instruction, there are some registers you expect to be the same. Right? If you set up a return address, you expect that to be the same. If you set up an argument, you might expect that to be the same. If you set up a return value, right? If you're jumping to a subroutine to get a value to come back to you, you would expect that value to change. So the saver list in our register file tells you which registers are whose responsibility. When you jump to a subroutine, which registers you can expect to be the same and which registers you might expect to change, right? So, for example, when you are jumping to a subroutine, you expect the return address to maybe change, because when I call JSR, one of the things it does, jump to subroutine, is it modifies the return value, because I got to be able to get back here. So if I'm jumping to a subroutine, I expect that before I jump, I will change the return value. That means it's my responsibility to put whatever is in the return value somewhere else, so that when I call JSR, it doesn't mess it up, right? If I got to assume somebody else is using it. And we have standard practices for that. We have a stack frame that does that. But it's the caller's responsibility to preserve the return address, because the caller, when I use JSR, is going to change the return address. On the other hand, the stack pointer, it's the callee's responsibility. If I call JSR, when that subroutine is done, I expect the stack to be in the same configuration as when I left it. I don't expect the stack to be different, because if it was, I'm lost. I can't, my frames are all screwed up. There's no way. So if I'm going to change the stack configuration, right, the stack pointer or anything else, it's my responsibility as a callee to put it back where I found it before I return from that subroutine. Global pointers and thread pointers are used globally, so they are not affected by this conversation. But then the real question is temporary registers and saved registers. These are two kinds of registers that people can use for temporary work, for work in progress, accumulation, and stuff like that. By convention, we say that the temporary registers are caller saved, just like the return address, right? When I call a program, I expect that the temporary register might change. So if I want to keep it, I'd better preserve it before I make a call. In the same way that I expect when I make my call, I'm going to change the return address. So I'd better preserve it before I mess with it. So I would preserve any temporary registers before I call the subroutine, with the expectation that the subroutine can mess with them as much as they want with no consequence. So those are caller saved. Callee saved, like the saved registers and the frame pointer, the callee, the subroutine, has to put them back the way they found them. So basically the difference is I don't have to put the temporary registers back, but I do have to put the saved registers back, right? I don't have to put the arguments back because I can use them as return values, but I do have to put the saved registers back. So the callee has to put the saved registers back, but can change the temporary registers. That's what this stuff is. And it'll take some time to get a handle on exactly how those things are done, but that's the general structure of the register file in RISC-V. I have a little picture of an example of a stack frame. If you haven't done stack stuff, if you haven't done parameter passing for subroutines, go and have a look at those videos. I'll probably make a video that's specific to parameter passing for RISC-V, but this is just a basic summary. The way that the stack grows in RISC-V is it grows towards smaller addresses. It grows up towards smaller addresses. The stack is full, which means the stack pointer points at a full value, in this case local variables. Saved registers, so this is a typical stack frame. Local variables, saved registers, the frame pointer, the old frame pointer, and then the return address. And typically, the frame pointer for a stack frame points at the return address. The other name for this is CFA, which is here, the canonical frame address, which is the value of the stack pointer at the call. And so when you call a subroutine, again, I'll give a full video on this a little later, but when you call a subroutine, the stack is at a certain position. That position, when you enter a subroutine, is called the canonical frame address. And so we set our frame pointer there, we put our return address there, and then we carry on. And that's all this frame means. This gives you an idea of what that is meant to look like. Okay, so that's the register file. Specifics of memory addresses and stuff when we talk about where the vector table is and stuff like that. We'll get to that a little later on. It's not that important for the beginning of learning how to write code in this. But that gives you an idea of how the register file is structured.